Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to go ahead and take all that we've now learned about quantum mechanical operators and revisit our good old friend, the free particle. So just as kind of a review, now we've got our set of quantum operators, our real wave functions. We can start applying them to real systems and situations. So again, good place to start is with our good old friend, the Hamiltonian. So this is probably the most important operator, as we expect most of our systems to have discrete quantized energies. And so as a result, most of our wave functions should hopefully be an eigenfunction of the Hamiltonian. However, as we've talked about before, things can get a little bit messy when we have a potential energy term. So today we're going to go ahead and start by setting this equal to 0 again. So this essentially just means we have a system where our particle has no real place to be. It can go wherever it wants because every place is as good as any other. So again, this is a classic vacuum situation. Physicists love it. It's a good starting point. However, when we do this, it generates a general form of the Hamiltonian of a form negative h bar squared over 2m, and then the second derivative with respect to position. Now, this gives us a multiple set of eigenfunctions for our Hamiltonian. However, the most general form is essentially going to be a summation of e to the ikx plus b to the e to the negative ikx. So again, from what we've seen before, certain amount of the movement going forward, certain amount of the movement going backwards. And one of the cool things is when we apply our Hamiltonian to, let's be honest, this kind of messy operator, wave function, what we find is that it does give us a single eigenvalue. So this means that while this isn't exactly the function we'd expect, it is indeed an eigenfunction of our Hamiltonian, with again an eigenvalue of h bar squared k squared over twice the mass of the system, where again, as a reminder, k is going to be related to the de Broglie wavelength of the particle. So again, if we know the de Broglie wavelength, we know a fair bit about the energy. We also know a lot about the movement of the system. And one of the reasons why we have a single eigenvalue is both of these components, these e to the ikx and e to the negative ikx, they both share the same energy eigenvalue. And so this is kind of a fun thing, is that you can essentially sum up any function, any set of functions that share an eigenvalue to generate a more general description of potential eigenvalues or eigenfunctions for an operator. So again, this is the most general form. Any other eigenfunction of the free of the kinetic energy Hamiltonian will be of this form in some way or another. However, energy isn't the only thing we care about. We often care about the momentum of the system, because if I know the momentum, I know a lot about the movement and the direction of the movement of the system. So we can find the momentum by taking the expectation value of the momentum of the system, where again, this involves applying our momentum operator to this wave function and then integrating over the complex conjugate with respect to position. So when we do this, what we can do is split up our wave function into the two separate eigenfunctions of the momentum, where this first component is an eigenfunction of the momentum, and so is the second component. But again, they're different eigenfunctions, which means that I've got a probability of finding the system moving in the positive direction by a squared and in the negative direction of b squared, with again, the momentum in each of those directions being kh bar and negative kh bar. So forward and reverse momentum. And again, these prefactors, again, give me the probability of finding the system moving in a given direction. If a squared is greater, it tends to move forward. If b squared is greater, it tends to move backwards. And the ratio of a squared to b squared is going to tell me a lot about the general directionality of the system. If the ratio is 1, the particle will tend to stand still. Now, we can then take this system and break it down into some essentially simplified cases. My personal favorite of which is when A is equal to B, because under this case, we have a shared prefactor, which can then essentially be pulled out front. And what this ends up, by pulling the A out front, what we're left is e to the ikx plus e to the negative ikx, which is the same as 2 cosine kx. So this gives us a total wave function of twice a cosine kx. So again, this shows that the system is going to be a standing wave with essentially an oscillation. Now, one of the cool things about setting the A equals to B is you'll notice that all of the imaginary components cancel out, and all we're left with is the real component of the system, so that our system will be entirely in the real plane, which again is a very kind of cool feature. Now, because it's a standing wave, it isn't too surprising that we're going to have a momentum expectation value of 0. And this can again be verified if you go back to our expectation value. We'll find out that if you have a probability, if you have a momentum of a squared kh bar minus a squared kh bar, you're going to have an average momentum of 0. So no net movement. So this is, again, a good limiting case. Another good limiting case is if we have unidirectional forward movement. So let's say I'm shooting an electron or a proton out of a particle accelerator. So if I do this, my particle moves in one direction. So I've got no movement in the reverse direction. So I'm going to set b equal to 0. At which point, my wave function then just collapsed to a to the eikx, and then what we have is unidirectional motion of kh bar. But one of the very cool things is no matter what the net movement of the system is, all of these particles share a given energy, which again is a very kind of cool feature. Now, one of the other things that I do kind of want to emphasize is because e to the ikx is a eigenfunction of the system, this means that this wave function should be orthogonal, or essentially cancel out any wave function with a different k. So again, this is a very kind of cool feature to see with the system, to see about systems, is be aware of your normality and your orthogonality, and you'll get a lot of information out of a good wave function. So next time, we're going to take this motion in one dimension and confine it a little bit into a box. Till then, take care.